So an important concept when we talk about reaction rates is the idea of catalysis. And to understand catalysis, we need to understand the energetics of what's happening during a reaction. So I've drawn two graphs here, one for an exothermic reaction and one for an endothermic reaction. And I want to step through them kind of slowly so you can kind of get the idea of how this works. So on the x-axis here, we have what we call a reaction coordinate, which is kind of a weird idea to think about. But you could just think about this as something that we can measure that tells us something about the progress of a reaction as it transforms things from reactants over to products. And over here, we have energy, the energy that's contained within our system. Our reactants are right here, and they have some sort of energy state to them. And our products are over here, and they have some sort of energy state associated with them. The difference between where we start off at with our reactants and where we end off with our products when it's lower, right? So our products now have a lower energy than the reactants. That means that it's exothermic. The energy that was lost moving from the reactants to the products was released as heat, and that's what exothermic means. What we haven't talked about yet is what happens in between these two things. And what winds up happening is there's always what we call an activation barrier. Okay, this is the energy that needs to go into a reaction in order for it to occur. And you can see that the energy of the system will be at its highest during this point when it's changing from one state to another. And this difference between the initial reactants and this state here is what we call our activation energy. That's the energy that we're going to have to put in order to have this happen. And what happens when we add a catalyst is we actually open up a new route for this reaction to take place. And that new route has a smaller activation energy. We don't have to put as much energy in to get the reaction up over this slump and have it come back down to the eventual products that we do. And because less energy needs to be added, the rate of the reaction starts to speed up during this process. Over here, we can see that our initial reactants are lower in energy than our final products. When we have this situation, we have to add energy ultimately to get the reaction to happen. And this is what we call an endothermic reaction, where we have an enthalpy that is positive, an enthalpy change that is positive between these two states. And the catalysis does the exact same thing though. It's still going to lower the required activation energy to get to this state, and the effect it's going to have is going to be exactly the same. It's going to speed up the rate of that reaction. So let's go through a few bullet points here that are important to understand about catalysts. So adding a catalyst to a reaction will increase the rate of a reaction by lowering the activation energy required. Catalysts do this by binding to the reactants, creating a lower energy transition state. And what the transition state is, what do these reactants and products look like in this intermediate stage? What is the geometry of that? And what's going to happen is the catalyst is going to bind to the reactants, and it's going to give them a new kind of geometry that is lower in energy but still looks very much like the original transition state. It does that through binding, and we've seen before that when bonds are made, that releases energy. And an important aspect of catalysts versus just a reactant is that catalysts participate in the reactions, but they're not consumed by them. Okay, you're going to wind up with the exact same amount of catalyst at the end of the reaction as you had at the beginning of the reaction. The reactants are going to bind to the catalyst, and then they're going to release to form the products, and ultimately you're going to have the same amount of catalyst. And for this reason, chemists really like catalysts too, because you only add a relatively small amount. Usually you get a large effect where the reaction's taking place much faster, and you're not consuming it. So you can often reuse catalysts a lot of the time. It's also important to note that catalysts are pretty much everywhere in all kinds of different systems. So we use industrial catalysts in order to produce all the commodity chemicals that we use. As we've talked a little bit before, enzymes are a form of catalyst that really make all of the chemical processes for life possible. And sometimes you'll even see catalysts used as chemical additives in themselves, right? For instance, some detergents and stuff actually add enzymatic catalysts now to help them break down the dirt and grime that would be in, say, your clothes or something like that.